Welcome back to geometry. This lesson is brought to you by Daisy, who thinks that she needs to chew this bone obnoxiously by me while I record, and I'm too lazy to move. So if you hear any annoying sounds, it's the dog. Lesson 2 is about some lengths of some segments in our circles, so chords and secants and tangents. And the first theorem of 4, the first theorem says that in the same circle, or if you had two congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So this picture shows that we have two chords that are the same length, which means that the measures of these arcs would be the same. And so this first example is one kind of like that. We see two chords that are the same length, and so that means that these arcs will have the same measurement. And they're giving me some info in the problem. It says that the measure of arc AC, the minor arc AC, is 150 degrees, so less than half the circle. And we're supposed to find the measure of arc AB. So you know how the whole circle has 360 degrees total? We've already used up 150, which leaves us with 210 degrees left for basically this major arc, right? And if I know that that's split into two congruent arcs, then I just take the 210, divide by 2. So each of those arcs would be 105 degrees. So that would be the measure of arc AB. And you can always go back and check, make sure all of those add up to 360. All right, the second one uses the if and only if part. So let's see. Oh no, it's still giving us the same thing. The chords are the same length, which means that these arcs need to be the same length and the same measure, which is what we're actually looking at. I think the measure of arc AC is 100 degrees, and the measure of arc ACD, so that's a major one, right? Because it has 3 letters from A through C, and then all the way to D is 190. Which just tells me that if 100 of it is from A to C, then this would be 90 degrees right here. Find the other arc measures. Well, since we had this congruent chord, congruent to this chord, that means that this arc's also a 90. How big is BD? Well, we've got 100 plus 2 90s already. How much is that? 280? So how much would be left out of our total circle? 280 already used up. Is that 80 degrees left for arc BD? So that was kind of a simple theorem. The next one is about segments of chords. So that's like two chords that intersect each other. And in this case, you'll see that it says EA times EB. So the length of EA is right here times the length of EB. So this little chunk times that little chunk is equal to, on the other chord, this chunk times that chunk. So that's kind of how I refer to it. So I'm just going to say that the 4 times the 6 in this example would equal the x times the 3, the other chord. So we'd have 24 equals 3x divided by 3, and x would be 8. And then you could always go back and check. 8 times 3, and that's the same as 4 times 6, so that works. This one's actually kind of a lot more complicated because of all the x's. So if you run across one of these, just stay calm. We just have to take a chunk times a chunk. So let me do the x times the x plus 4. And that would have to be equal to this chunk times this chunk. So x plus 2 times x plus 1. And that's kind of intimidating because we have to remember our algebra. So step 1 is to distribute that x. X times x is x squared, x times 4. And then on this side, we're going to have to FOIL. So x times x times 1. 2 times x, 2 times 1. X squared, 1x, 2x, and 2. Let's just simplify that, add those like terms together. Beautiful. And at first it looks like I might have to use the quadratic formula or something, but actually this time if I subtract the x squared from both sides, it kind of takes care of that issue for me. So it's actually just they call it a linear equation because there's no squareds in it. Subtract 3x from both sides. What would that leave me? 1x over here. So x would equal 2. That wasn't too bad. I always like to go back and check. So if I plug a 2 in right here and a 2 in right here, I've got 2 times 6. If I plug in a 2 in right here and a 2 in right here, I've got 4 times 3, and that checks out. So 12 times 12, or 12 equals 12, beautiful. All right, this one is just a little bit more complicated because we have parts of the secant line, right, coming out of the circle. So this isn't showing the entire secant line, it would extend. So we're just kind of looking at secant segments, they call them. If two secant segments share the same end point outside the circle, then the product of the lengths of one secant segment and its external segment equals the product of the length of the other secant segment and its external. That's so much. Did you catch that? So I just have a different way of saying that makes more sense to me. So here's the little equation. It says that EA, so this little outside part, times EB. EB is this whole thing, right? So what I say is that the outside times the whole thing, and that's actually how I refer to this. Outside times whole equals, and then on the other side, EC times ED. EC is the outside and ED is the whole thing, equals outside times whole. So you'll hear me say that a lot because that's how I refer to this theorem. So maybe let's do a little example of that just so you can see how it works. So this first example down here, so do you see how the 6 is on the outside? So we're going to take the 6 times the whole thing. And so what are we going to have to do? We're going to have to add those together, right? Wouldn't that be 15? The whole thing is 15 long. And actually that's one thing that I usually would have you add to these notes. The whole thing, you actually want to add them together, right? Because this whole thing would be 9 plus 6. So anyway, outside times whole equals, and on this segment, the outside is the 5. And how long is the whole thing? How far is it? I would call that x plus 5. Make sure you add to find the whole length. And now we're just going to solve that baby up. So we've got 6 times 15 is 90. Distribute that 5. Subtract 25. Divide by 5, and I should get 13. Again, I like to check that. So I would take 6 times 15 was outside times whole from that one. And outside, and if this is 13, how long is the whole thing? 13 plus 5 would be 18. So 6 times 15 equal to 5 times 18. They're both 90, so we win. This last theorem of the day, you know, they have it as a separate theorem, but I like to think of it the same way as the other one. So the only difference here is that this time it's a secant and a tangent that are sharing this outside point. And so you can see that EA, they call that a tangent segment because they didn't draw the whole thing, right? So EA, they say that, well, I like to think of it as the outside times the whole thing. It's just that the outside and the whole thing happen to be the same length because for a tangent, the entire thing is outside. I don't know if that makes sense to you, but it's always made sense to me, and then I don't have to remember another theorem. So outside times whole, that's the EC times ED. So I like to still think of it the same way, that the outside times whole equals, and that's for the tangent segment, the outside times whole, and that's for the secant this time. And like I said, the only thing is like the outside and the whole for this tangent segment are both the same thing. So we're taking the same thing times the same thing. Let's do an example and see if that makes any sense. So here is our tangent segment DC. And so how much is outside the circle? 24 of it. And how much is the whole thing? The whole thing is outside, so 24 times 24. Or you could write that as 24 squared, right? All right, now for our other segment, we're going to take the outside, is 16 times the whole thing. What would it be? Say it in your head or out loud. A lot of people tend to say 16x, but you have to remember that it's 16 plus x. So again, if you need to remind yourself that to find the whole thing, we need to add both of the segments together, yeah? All right. Honestly, you guys, it's the setup that is the main thing here, because after that, it's just practicing your algebra skills, knowing how to do some multiplication, distributing that 16. All right, subtract 256. Do you have a calculator? Divide by 16, and I'm getting 20. And one more time, I'm gonna check that. So if this little chunk is 20 out here, 24 times 24, I know that's 576. And is that equal to the outside times this whole thing? The whole thing would be 36, yeah? 16 times 36, looks like that checks out. So that's just a nice way to check your answers. All right, let me know if you have any questions. Good luck.